problem I want to solve for you today is a simple problem on mass conservation, but it has details which could help you to solve other problems in other chapters of thermodynamics. Well, the problem tells us that there is a rigid tank. And when it says it's a rigid tank, in the thermodynamic language, a rigid tank means that V equals constant. It means that volume is the same. Of course, if it is rigid, could it mean that mass is the same? Well, mass is the same does not need it to be rigid. The constant mass means that there is no mass coming in or going out. So a rigid tank with no entry or exit would mean that mass is constant. Now, it takes two cases. One is that the volume is 4 liters, and the other case, this is case A, and the other case, case B, is that the volume is 400 liters. So these are the two cases that we studied. Now, what there is inside the tank is water, and the water is some liquid and some vapor. The mass of water, that means the sum of liquid plus vapor, M equals 4 kilograms. There's 4 kilograms of water, both liquid and vapor together, and the temperature T1 equals 50 degrees C. And this is the initial condition of the problem. Now, we heat this tank, and the final condition could be liquid or could be vapor. The problem tells us that the final condition, there is either liquid filling the tank or vapor filling the tank. I mean, when we heat it, two alternatives are possible. First, the pressure goes up, and as the pressure goes up, the vapor turns to liquid and liquid fills all the tank. Or alternatively, liquid vaporizes and vapor fills the tank. But at the end of the story, there is only one phase, and it asks us what happens and which is that phase, what's the pressure, and what's the temperature. So what it wants is P2A, T2A, or P2B, and T2B. These are what the problem wants from us. Our process for solving such problems, as usual, there are 5 steps. And the 5 steps are: 1, decide on the boundaries that you want to solve, decide on the boundaries, decide what do you want to solve. You don't want to solve all the problems in the world. You just want to solve step, a special area, and decide on it. Then find fluid properties, find properties. 3, the third step is to draw a diagram. 4. Simplify conservation equations. Simplify conservation equations. And finally, get everything together to reach a final solution and whatever the problem has asked from you. So move towards problem requirements. And what I shall do is to follow these steps to solve this problem. And the first step is very, very simple. I have to decide on a control volume and control mass. And what I do is that I select whatever water, either vapor or liquid, that is inside this tank. And this is my boundary. Then I will do all the rest of the calculations for just this boundary and whatever there is inside this boundary. Well, the next step is properties, and what we are told is that the temperature, the initial temperature is 50 degrees C. So what we do is that we go to saturation tables for water, since whatever there is, the problem is of water. We go to saturation tables for water and find water properties. Well, we have it here, and for temperature 50 degrees C, the saturation pressure is 12.352, and I just write it down here for T equals 50 degrees C. Saturation pressure P sat equals 12.352 kilo Pascal, and the Vf, as it is here, Vf equals 0.001012 cubic meters per kilogram. Vg is the next column, and that is 12.026, 12.026 cubic meters per kilograms. And please remember to write down the units. It's very important that everything should have units here. And what I would do here is just to look at the next three columns, and although the problem doesn't involve it for the time being, but I will look at the next three columns to see what happens for other properties, because finding them and treating them is very similar to specific problem. So I would read UF equals 209.33 kilojoules per kilogram. This is the internal energy, and I will read it from this column. The next column is UFG, or I would jump to the other one. I would jump to this one first. This one is UG, which is the internal energy for saturated vapor, and that is 24. UG is 2442.7 kilojoule per kilogram, and UFG, which is the difference between UG and UF, is 2233 0.4 kilojoule per kilogram. This book doesn't give us any value for VFG, but it's not difficult to calculate it. VFG equals VG minus VF, which would be 12.025 cubic meters per kilogram. That I have written a different color since I've calculated it and I have not directly read it from the table. Now, this is the TV diagram, and on it, what we know, we would put the properties of water, regardless of what our problem is, because it doesn't depend, our properties of water does not depend on our problem. They are fixed, okay? So the first step is to decide on the temperature. We know the temperature, and this is, say, 50 degrees C. So what I would do is to draw the 50 degrees C saturation line, and this is the constant pressure line. And what we know, what we have learned is that P here, P equals 12.352 kilopascal. That's our pressure, and this is the 50 degrees C. And what we have read here for it, we know that here the specific volume VF equals 0.001012. This is this point. And we also know that for this point, Vg equals 12.026, and they are all cubic meters per kilogram, as it is written here. So these are water properties, nothing to do with our problem. We know that our problem is on 50 degrees C, but these properties, these values are water properties irrelevant to this problem or any other problem. They are water properties. Okay, there's one more point which, if we write its properties, it would be very helpful to us. So, and this is the critical point. What are the critical point properties for water? We could also read them from different tables in the book, the same table as I used just now. And what we know for this point is that P equals 22.064 megapascal, and T temperature is 373.95 degrees C. Added to these two, there's one more property which is of interest to us, and that property is a specific volume. And what it tells us is that this specific volume, V at critical point, is 0.003106. This is V at critical point. Okay, these are properties of water. Now, where our problem stands and our knowledge for specific volume and temperature tells us where do we stand. We are at initially we are at 50 degrees C, so we could be here, we could be between these 2 points, and we could be on the superheat vapor point. But how do we decide on it? We shall know what specific volume is, and when we decide on the specific volume, then we would know where in this curve do we stand. Well, we are told that at condition 1a, volume is 4 liters and mass is 2 kilograms. So I would just write it here. A specific volume for condition 1A. Condition A is because the volume is 4 liters, and 1 because no process has happened yet. It's just the starting point. V1A would be is volume divided by mass, and that is 4 liters, which means 4 times 10 to the minus 3 to turn it into cubic meters, and divided by mass, which is 2 kilograms. And therefore, V1A would be 0.002 cubic meters per kilogram. That's the initial specific volume. What happens to V1B? V1B would equal 400 times 10 to the minus 3 and divided by 2. And therefore, V1B would be 0.2 cubic meters per kilograms. Well, we have our initial conditions. This is our problem. Okay, this is our problem. The difference is that previously, whatever I put down on this diagram was water properties. Okay, water all from table. Now we have our problem, and what it's telling us is that initially our specific volume is 0.002. So we are on temperature T 15 degrees C. Here Vf is 0.001, so our specific volume in case A is larger than this and smaller than 0.003. So point 1A would be somewhere here. This is point 1A. What happens to point 1B? Point 1B still is on the 50 degrees temperature, but at the same time, its specific volume is 0.2, still far from 12.026. It would be somewhere here. Let's put it here. Of course, it is closer to the critical point if I want to draw it proportionately, but as it is, I will draw it just like this. It is point 1B. Now we have our initial conditions, and what you have to do is to see what the process is. And what would tell us about that is the mass conservation law. Well, I shall solve the rest of this problem in part B. Thanks for watching and cheers.